Yes, this is my fifth lecture on King theory. In fourth lecture, we have discussed the model, King first model MM1 infinite FCFS, and we have derived the differential equation for the case n greater than 0. Today I'll derive the differential equation for transient case when n is equal to 0, and then we will consider the steady state difference equation and will solve these equations to find the characteristics of the model. Now I start. The differential equation which I have derived in my fourth lecture is given by this: P dash n t is equal to minus lambda plus mu p n t plus mu p n plus 1 t lambda p n minus 1 t n greater than or greater than 0. So this is the case when n greater than 0 and number of units in the system. And now I'll write the differential equation for the case n is equal to 0. Now if you see the event of no unit in the system at the time t plus delta t, this event can happen in any one of the two mutually exclusive ways. The first way or the first event is no arrival in time t, no arrival in delta t. Question of service does not arise because up to this there is no unit in the system. Or the same event of no unit in the system at the time t plus delta t can happen in this way: one arrival in t, no arrival in delta t, but one service in delta t. So you see here again one arrival in t, no arrival in delta t, one service in delta t. Therefore, after the elapse of time t plus delta t, there is no arrival in the system. And now, as this event of no arrival or no units in the system at t plus delta t can happen either in this way or it can happen in this way. So therefore the two events, suppose we designate this event by A or this event by B. So the two events are mutually exclusive, and here R means the union. So we know if the events are mutually exclusive, then probability of their union is equal to sum of their separate probabilities. So therefore, taking probability on both of the sides, when we do write the no units in the system, event of no units in the system is equal to union of this event and this event. Now taking the probability on both of the sides, probability of this event is equal to probability of A union B, or probability of A or probability of B. So then this is the sum of the two probabilities. So here it is union, here it is union, and union means plus the probability of the A, two events A union B, if the events are mutually exclusive. So then the probability of A union B is equal to the probability of A plus probability of B. Because we know the theorem is this on probability. Probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. But here, as the two events A and B are mutually exclusive, A intersection B is null event and the probability of the null event is 0. So therefore, probability of A union B is equal to only probability of A plus probability of B. So using that theorem, the probability of this plus probability of this. Now the probability of this event, no arrival in time t, no arrival in delta t. This is the simultaneous occurrence of this event and this event. And if it is the simultaneous occurrence of the two events and they are independent, then probability of their intersection is equal to product of their separate probabilities. So simultaneous occurrence of this is probability of this first part into probability of second part, and as we know, the probability of no arrival in time t is designated by P0t, and the probability of no arrival in delta t, as you know, the probability of one arrival in delta t is lambda delta t. The probability of one arrival in delta t is lambda delta t, and probability of no arrival in delta t is 1 minus lambda delta t, because it is the alternate event and those two events union probability is 1. So here this first part probability is given by this P0t, probability of no arrival in delta t 1 minus lambda delta t, plus R means plus, and then the probability of this B, I was saying this event to be B, designated by B, but this B consists of three event simultaneous occurrence. One part this, one arrival in T, second part no arrival in delta T, one service in delta T. So therefore, the simultaneous occurrence of these three event probability is given by product of their separate probabilities, that is probability of one arrival in T, P1T, probability of no arrival in delta T, 1 minus lambda delta T, probability of one service in delta T, that is mu delta T. So plus 0 mu delta T, this one 1 minus lambda delta T, mu delta T. And now in this also, in the derivation of this, we have supposed that second power of delta T or delta T square is negligible, as delta T is very very small. Also higher the terms containing higher power of delta T or ignorable. So ignoring those terms, we have obtained this. Now similarly in this case, you see here P0t lambda delta T P0t plus P1t mu delta T. But this term, product of lambda delta T and mu delta T, is the term containing delta T square. So is 0. Delta T square is taken to be 0. Delta T cube is also taken to be 0 here. So now this equation for n is equal to 0 case becomes P0t plus delta T is equal to P0t lambda delta T P0t plus P1t mu delta T, or shifting this P0t on the left hand side and dividing the whole equation by delta T, we obtain this P0t plus delta T minus P0t over delta T is equal to minus lambda P0t plus mu P1t, and now letting delta T tending to 0. So what is the right hand side? By the definition of derivative, it is the derivative of P0t. So therefore, in steady state P and T, we get this now. This left hand side is the derivative of P0t, that is P0 dash t is equal to minus lambda p0t plus mu p1t. So here we do have now equation number 1 and 2. These are 1 and 2 are differential equation for transient case, where the operating characteristics of the model depend on time. So these two equations for transient case, as by definition of the transient, I have already defined transient case. So 1 and 2 are the differential equation for transient case of Quine model first and 1 infinite FC, Fs or Fi, first in, first out, we can say. So now, in case, steady state case, in steady state case, the characteristic independent of time. So therefore, you see here d by dt p and t is equal to 0, or as t tends to infinity. Now t has no meaning. P and t is to be replaced by Pn only. It is not P and t. P and t is the probability of n units at time t, but now it is independent of t, so this is to be denoted by Pn. So now the first equation, first differential equation, or now in case of steady state, it becomes only the differential equation, not the differential equation. Putting left hand side is equal to 0, we do have minus lambda plus mu Pn plus mu Pn plus 1 plus lambda Pn minus 1 and greater than 0. And this one, taking this to be 0, left hand side 0, right hand side minus lambda p0 plus mu p1. That is 0 is equal to minus lambda p0 plus mu p1. So these are the difference equations of the Quine model Mn1 infinity FCFS. And in steady case, so now we solve the steady case difference equation using iterative method. So here you see we are giving name to these two difference equations for steady state case as equation number 3 and equation number 4. Now from equation 4, when n is equal to 0, we have p1 is equal to lambda by mu p0, and now using n is equal to 1 in equation 3, substituting n is equal to 1 in this equation 3, we have n is equal to 1 in equation 3, and p1 is equal to, this is from 4, lambda by mu p0. Now substituting this in n is equal to 1 in equation 3, we do have minus lambda plus mu p1 plus mu p2 plus lambda p0 is equal to 0, or minus lambda plus mu into lambda by mu p0 plus mu p2 plus lambda p0 is equal to 0, or minus lambda square by mu plus lambda p0 plus lambda p0 plus mu p2 is equal to 0. And simplifying this, we do have, simplifying this, p2 is equal to lambda by mu whole square into p0. So we have obtained up to now the value of p1, the value of p2. Now similarly, using n is equal to 2 in equation number 2, we have this n is equal to 2 in 3, we do have this equation minus lambda plus mu p2 plus mu p3 plus lambda p1 is equal to 0, or the equation is given by this, or simplifying this, or we do have now P3 is equal to lambda by mu whole cube P0, and then P1 is equal to lambda by mu, here 1 power P2 is equal to lambda by mu square P0, and P3 is lambda by mu cube P0. So then similarly for integer value of n, Pn is equal to lambda by mu whole to the power n P0, or you can also obtain this result by using mathematical induction. There is no problem. Mathematical induction you can use, and you can say that the rule is up to, for any integer value of n, Pn is equal to lambda by mu whole to the power n into P0. Now the question is, we are getting P1 in terms of 0, P2 in terms of 0, P3 in terms of P0. What is the P0 here? It is quick first model, not the Poisson process. So here, to obtain the value of P0, we use the fact that in any situation the sum of all probabilities is 1. So we use this fact. Using this fact, we have now n is equal to 0, summation to infinity Pn is equal to 1, or P0 plus P1 plus P2 plus P3 plus and so on is equal to 1. Now substituting the value of P1, P2, P3, P0 plus lambda by mu, P0 plus lambda by mu whole square, P0 lambda by mu cube P0 is equal to 1, or P0 in bracket 1 plus lambda by mu whole square, lambda by mu whole cube and so on is equal to 1. So here lambda by mu is less than 1. You know in geometrical progression, if it is the progression like this, 1 plus r square plus r cube, and r is less than 1, then sum of infinite terms is 1 over 1 minus r. Here r is equal to lambda by mu. So therefore we have now 1 P0 into this, lambda by mu less than 1. So this is P0 into 1 over 1 minus r. Here r is lambda by mu is equal to 1, or P0 is equal to 1 minus lambda by mu. So now substituting this in Pn, in the term having the value of Pn, Pn is equal to lambda by mu whole to the power n 1 minus lambda by mu. So this is the probability of n units in the system, where lambda is the mean arrival rate, mu is the mean service rate. Now to find the characteristics of this model, the first characteristic in this queuing model is average number of customers in the system, or expected number of customers in the system. You know, if x is a random variable, discrete random variable, then what is the expected value? Ex, that is equal to summation of x px. But here x is not a variate, but n is the variate which is counting the number of units in the system. So this is international symbol to designate the expected number of customers of the units in the system LS, and Ex, expected number of units in the system, that is equal to summation of x px, but here it is n into Pn, variable is n, corresponding probability function is Pn, and now n is equal to 0 to infinity. Let us put the Pn answer. Pn is lambda by mu whole to the power n 1 minus lambda by mu, and in this way this is now taking 1 minus lambda by mu out side of the summation. because summation is for n, not for lambda and mu. We can take this term 1 minus lambda by mu outside of the summation. Taking this outside of the summation, we do have now n is equal to 0 to infinity and lambda by mu whole to the power n. And now substituting here n, taking this n, 1n, lambda by mu 1 minus lambda by mu and lambda by mu to the power n minus 1. We have taken here 1 lambda by mu outside. So now it is the power n minus 1. Actually here we are writing only n is equal to 0 to infinity. The first term will be 0. The correct summation here n is equal to 1 to infinity. So this is now this is this, n is equal to 1 to infinity and lambda by mu whole to lambda by mu out 1 minus lambda by mu, and opening this summation n lambda by mu whole to the power n minus 1. So let us put in this n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, and then lambda by mu 1 minus lambda by mu bracket 1 plus 2 lambda by mu when n is equal to 1, lambda by mu whole to the power 0 gives you 1. So this is 1 only. The second term when n is equal to 2 will be 2 into lambda by mu. 2 minus 1 is 1. And then 3 n is equal to 3 lambda by mu whole square plus so on. So if you see here, what is it? This can be adjusted as the binomial theorem result for negative index. If you open, you find the value of this 1 minus lambda by mu raised to the power minus 2, as you have done for binomial index. 1 minus x whole to the power minus 2 is 1 plus 2x plus 3x square plus so on. So similarly here 1 minus lambda by mu whole to the power minus 2 is lambda by mu 1 minus lambda by mu, and now taking this minus 2 power in the denominator and simplifying it. Now 1 power of this is 2 power, 1 power will be cancelled, and now it is lambda by mu 1 minus lambda by mu 1. Now 1 power we will have of this 1 minus lambda by mu in the denominator. Therefore the expected number of units in the system Ls is given by lambda over mu minus lambda over mu minus lambda. Now average queue length, or the expected number of units or the customers waiting in the queue. We are not finding the expected number of units in the system. We are finding the expected number of units waiting in the queue, expected number of customers waiting in the queue. So now what is the expected number? LQ, the symbol denoted by LQ here, or EN, where m is equal to n minus 1, because if n denotes the total number of units in the system, then one will be getting service, one service station is there. So in Q there will be n minus 1 units. So therefore we have to find the expected number of units in Q only. So n is equal to 0 to infinity npn, where n is equal to n minus 1, or n is equal to 1 to infinity, because here also you see n is equal to 0, we get 0 answer. So it is start from n is equal to 1. Similarly here n is equal to 1 to infinity n minus 1 pn is equal to n is equal to 1 to infinity npn. This is npn is actually en, the expected number of units in the system, minus n is equal to 1 to infinity pn, or this is equal to en minus n is equal to 1 to infinity pn, or is equal to en minus 1 minus p0. Why 1 minus P0? Because sum of all probabilities is 1. So we are taking from 1 to infinity. This is 1 minus P0, and that is equal to lambda over mu minus lambda minus 1 minus lambda by mu, or this is lambda over mu minus lambda by mu, that is lambda square over mu into mu minus lambda, or LQ is equal to L square over mu into mu minus lambda. So this will give us the expected number of units waiting in the queue, not in the system. It does not include the unit which is getting service. It is the expected number of the units of the customers waiting in the queue. And then in my next lecture, I will derive this average length of non-empty queue. And that will be equal to expected value of m greater than 0, and that is equal to expected value of m. This is like conditional mathematical expectation, that is equal to em divided by probability of m greater than 0. So I will derive it in my next lecture, which is in number 6. This is my 5th lecture.